All right, final topic in Calculus 1. We are going to be talking today about the substitution rule. Welcome back to 3 Deviations. So, as I said, we are going to be talking about a new rule for anti-differentiation, for indefinite integration, and then this will be applied to definite integration, but we're going to talk about that later. Today we're going to be devoting some time to covering some foundations for this idea. This is probably the most complex idea we've talked about in a while. We did a little bit of complex stuff talking about all those Riemann sums, but that was just tedious. This is actually some new work that we need to do. So one of the things about the substitution rule is that it's fairly dependent on your choices. So what you choose to be your change of variables. But we'll talk about that later. First, we're going to take a little bit of a trip down memory lane. If you remember the chain rule back from Unit 2, the chain rule was a tool for taking derivatives. So this was one of our many universal rules. This said that if I have a composite function, if I have the derivative of f of g of x, if I want to take that, then what I will evaluate for is f prime of g of x times g prime of x. Now, just to refresh your memory, let's do a simple example. Let's take the derivative of something, how about sine of 2x? If you remember this 2x, we picked 2x as our inner function. Then we have sine on the outside, so our derivative is going to be cosine of 2x times our inner derivative, which is 2. So we get 2 cosine of 2x. So that's how the chain rule works. So we can easily differentiate these functions with the chain rule. I said a little bit earlier in Unit 4 that integration was a slightly different animal when dealing with reversing the differentiation. We're going to see that today, that it is a little bit more tricky. All right, so now let's actually talk about the substitution rule, which, as you may have guessed from my reference to the chain rule, is actually the opposite of the chain rule. So the substitution rule deals with taking the indefinite integrals of composite functions. So the substitution rule says that if I want to take the indefinite integral of f of g of x times g prime of x with respect to x, then I can rewrite that with a change of variables setting g of x equal to u as the indefinite integral of f of u with respect to u. All right, so a couple things to talk about here. First of all, we should notice that we are making a change of variables. So we're making a change of variables from this g of x to a u. So we're changing variables here, going from x to u. And this change of variables should allow us to usually make this integral here, f of u du, something that's very easy to do, something that would be on the table maybe, or with some manipulation that we could definitely deal with. Another thing to mention is that this f function, whatever, I know this is a composite function, but it should just be mentioned so that you can easily recognize what your g of x, what you should set your u to be equal to. We're looking for the inside of something. So the f is usually going to be a big operator of some sort, like a square root or a trig function. And then the g of x is going to be what we set our u equal to, and that's going to be some sort of argument of a trig function or a logarithm or an exponential. And then also, we are actively seeking out where we can find the derivative in our integrand of that function inside of the operator. All right, so this all seems fairly abstract, and it is pretty abstract, but I think an example will clear it up. So we're going to do a really simple example. We are going to integrate 3x squared times the square root of 1 plus x cubed times dx. All right, so this actually makes it really easy to determine what we should make our change of variables as, what we should substitute in. Well, we have this square root operator. We have this big guy here. So this automatically tells me that my u should probably be this. but I should make sure by differentiating it and see if I can find the derivative of this function in the rest of my integrand. So if I have 1 plus x cubed, then the derivative of that is going to be 3x squared. And, well, what do you know? 3x squared is also in my integrand. So if I set u equal to 1 plus x cubed, and then I have my derivative du equal to 3x squared with our differential dx on the end, then I'm going to be able to substitute everything back into my integrand, and I'm not going to have any x's left. And that's what's really important about a change of variables. You're making sure every variable gets switched to u. So if I plug in u, that's going to deal with that. That's going to go in there. And then if I have my 3x squared dx, well, I'm going to have my 3x squared going in right in there. So I'm going to have my integral fully in terms of u now. So when we plug in all of this stuff that I have in my bracket there, we are going to be left with the indefinite integral of the square root of u with respect to u. Now this is something that looks a lot better than this, at least from our perspective as a Calculus 1 student. So now what we can do is we can evaluate this integral as an elementary integral. We know how to evaluate the integral of the square root of our variable. That just becomes 2/3 times u to the 3/2 power. All right, now we have our u, and we've solved our integral, but now we just need to reverse substitute. So we remember u is equal to 1 plus x cubed. So all that's left is we need to plug in this u into our answer. So that's going to leave us with 2/3 1 plus x cubed to the 3/2 power, plus our constant of integration. So that's how a substitution works. It allows us to deal with these more complicated functions to integrate them. So, of course, this is something that probably seems very new, but as you do more of these integrals and you do some more challenging ones, these substitutions should almost be mental. I put in all of these brackets here just to show you how to do it the first time. We're going to do tons of examples like this, but once we're done here, you should be thinking, oh, I see an inner function and I see its derivative. I'm going to set u equal to 1 plus x cubed, and then everything's going to be nice. I'm just going to be left with the integral of the square root of u, find that integral, plug back in x, add a plus c, you're good. So that is a very simple example. Now I just want to recap with a methodology, with a guide to how you perform a successful change of variables in an integral. So, as I said, in the integrand, we are looking for a composition of functions. We're looking for an operator, the inside of an operator. We're looking for what to set our u equal to. We're also then going to look for the derivative of the inner function somewhere else in the integrand. So I'm looking for a derivative of the inner function. As you remember the chain rule, when I take a derivative with the chain rule, I'm left with the outer function's derivative outside of the inner function, and then the inner function's derivative is tacked on at the end. That's how the chain rule works. And we're really looking, when we're doing these integrals, at functions that have been differentiated using the chain rule, and we need to reset that with an integral. So next, what we are going to do is we are going to find our change of variables. So that's usually going to be the inner function. Then we're going to find our u. And then we are also going to differentiate that as well to find our du. And sometimes we need to do a little bit of manipulation with the du in case there are any constant terms that we need to change. So that will usually end up with having an operator, u inside, du, and then sometimes a constant in front of the integral. We also then want to perform that substitution, and that should ideally result in an elementary integrand, one that we can do right from the table, maybe with a tiny bit of manipulation. And then, once we've solved that integral, all that's left is to change everything back to u, and change everything back from u to the original variable. Then we are good. Then we know that we have done a successful integral. All right, So that's the basic introduction to the substitution rule. So in the next video, we are going to do some examples, and we're probably going to follow that up with even more videos with examples, because this is something that we need to get down hard before moving into some more challenging topics in Unit 6 and 5. So we will talk about that later, and we'll be cranking out some examples. Also, we have been working on some shorter videos. Now that we're talking about indefinite integration with substitution, we've got a playlist called the Daily Integral, and a lot of those are substitutions. So if you're having trouble with solving an integral, then maybe you should check those out. We're trying to cover a lot of ground with those integrals, so you'll probably be able to find the one that you're looking for. All right, we will see you guys in the next video. Have a good time studying some substitutions. Bye-bye.